As explained during the main program, there's so much to cover on ASHRAE 62.1 that we recorded the supplemental content. Dennis is going to explain all the requirements in sections 4 and 5 of the standard, and Paul will explain how the standard allows for design based on average population and walk through a few examples. And finally, John will expand on his 3-zone example by going step by step through the Appendix A calculations for systems with a secondary recirculation path. So Dennis, I guess you're up again.
Okay. Section 4 addresses outdoor air quality. It requires designers to assess the outdoor air both regionally and locally. The regional compliance status with the National Ambient Air Quality Standards must be determined. In the U.S., compliance status is either attainment or non-attainment with the national standard for criteria contaminants. Go to the EPA website to look up the status for each outdoor contaminant in the region of the building site. Local air quality must also be assessed by conducting a simple observational survey of the building site to identify any local contaminants or potential sources. Go to the building site, look around, and document any potential contaminant sources observed. No measurements are required. The documentation requirement for Section 4 includes basic information which must be discussed with the owner when making decisions related to outdoor air cleaning and intake location. Section 5.1 requires that the system be designed to accommodate air balancing, which helps ensure that the outdoor airflow rates required can actually reach each zone at any load condition. Also, if the ceiling or floor plenum is used to mix recirculated return air with outdoor air, the design must ensure that mixing occurs. This one seems like it might be a little hard to enforce. I know that it was included primarily to address systems with water source heat pumps mounted above the ceiling. Traditionally, these systems merely dumped 100% outdoor air into the ceiling plenum from a central shaft. But to comply with this requirement, outdoor air must be ducted in the plenum and discharged near each terminal unit or into each occupied zone. Finally, this section requires documentation of balancing requirements and air distribution design assumptions. Remember that balancing is important, and it's usually best to duct outdoor air directly to each zone in a 100% outdoor air system. Section 5.2 simply requires that exhaust ducts conveying potentially harmful contaminants must be operated at negative pressure. The exhaust air must be pulled through the duct, not pushed through it. This means that the fan discharges to outdoors. Section 5.3 requires controls to enable and disable fan operation. It also requires controls to ensure that the system maintains at least the minimum outdoor airflow needed at any load or dynamic reset condition. To accomplish this without simply overventilating and using excess energy, constant volume air handlers for both single zone and 100% outdoor air systems may need modulating dampers or modulating injection fans, especially if they use high efficiency filters. And all VAV air handlers need modulating dampers or injection fans, whether they're applied in a single zone or 100% outdoor air system or a multiple zone system. Of course, although not yet required by Standard 62, most designers know that most VAV systems need to sense outdoor airflow as a means to modulate the dampers or fan motors. Section 5.4 requires that air distribution equipment and ducts be constructed using materials that don't support the growth of mold or bacteria and won't erode at normal duct velocities. These materials must pass a mold growth resistance test and an erosion resistance test, both defined by UL 181. Most matte finished duct lining materials used these days meet both of these UL tests. The purpose of Section 5.5 is to reduce the introduction of contaminants from outdoors. It includes location requirements for the outdoor air intake, rain entrainment and rain intrusion limitations, snow entrainment provisions, and bird screen provisions. Today I'll discuss intake location. Table 5.1 lists minimum separation distances between the outdoor air intake and potential outdoor contaminant sources. For instance, Class 2 air, like toilet or kitchen exhaust, must be at least 10 feet from the intake. Combustion vents must be at least 15 feet away, and cooling tower exhaust must be at least 25 feet away. Now remember, these are minimum distances. More separation is always better. Section 5.6 requires that contaminants from non-combustion sources, like printers or copy machines, must be captured locally and exhausted. They can't be allowed to simply mix with return air and recirculate throughout the building. Section 5.7 addresses indoor combustion processes. Indoor combustion appliances must have an adequate supply of makeup air to support combustion, and the products of combustion must be removed. That's why gas water heaters need exhaust outlets and gas stove tops need exhaust hoods. Section 5.8 addresses particle filters. Large particles can accumulate on wet surfaces, reducing free area and sometimes plugging coils. Particles on wet surfaces can support mold and bacteria growth, and reduced free area can increase velocity through coils. Dirty coils can decrease airflow in constant volume systems and increase fan horsepower in VAV systems. Dirty coils can also increase water droplet carryover and promote mold and bacteria growth downstream of the drain pan. The standard requires the installation of at least MERV 6 filters upstream of any wet surface device. According to ASHRAE Standard 52.2, MERV 6 filters remove between 35 and 50% of particles in the 3 to 10 micron size range, so they keep the coils cleaner longer than traditional low-efficiency filters. Section 5.9 encourages dehumidification to prevent problems associated with damp buildings and positive building pressure during mechanical cooling operation. Relative humidity above 65% can lead to high water activity level in porous materials, which can lead to mold growth. And negative building pressure during cooling operation pulls moist outdoor air into the building envelope, which can lead to mold growth within the walls or in the occupied zones. To reduce potential humidity-related problems, system designs must be analyzed at the design dew point condition without solar load. If the psychrometric analysis shows that zone relative humidity rises above 65%, the system must be enhanced with reheat, for instance, or a different system must be used, single zone VAV, for instance. Note that many constant volume systems with sensible-only thermostats may not meet this design requirement. In addition to dehumidification, systems must be designed to limit the infiltration of moist outdoor air into the building. Mechanical systems should be operated to ensure positive building pressure during dehumidifying conditions, but the standard simply requires that intake airflow exceed exhaust airflow whenever the system is dehumidifying. Section 5.10 addresses drain pans, which are required beneath all condensate-producing devices. Condensate management systems reduce the potential for flooding or water droplet carryover into the unit or the ductwork. Standard 62 includes several prescribed drain pan design requirements as well as some performance requirements. Drain pans must have a minimum slope of 1/8 inch per foot. The drain opening must be located at the lowest point in the drain pan, and the opening must be large enough to ensure that all of the condensate drains out. For draw-through arrangements, where the pressure above the drain pan is negative, the drain opening must be sealed in some way to allow condensate to drain freely while preventing the ingestion of air and associated spitting and overflow problems. And of course, the drain pan must extend downstream far enough to catch most water droplets that blow off the coil at design air velocity. Of all of these requirements, a drain seal that really works right is probably the most important. This graphic might be too small to see, but it shows 3 common P-trap designs. The one on the left is sort of a U-trap. It doesn't work because the drain opening is too close to the floor. The trap isn't deep enough or tall enough to store enough water to maintain the seal when the fan is on. The unit ingests air, which spits condensate into the airstream and allows the drain pan to overflow. The middle design doesn't work either. It's tall enough, but not deep enough. Again, it doesn't seal when the fan is on, so spitting and overflow result. A trap might not actually be designed like this, but if it includes a T-fitting and a plug for cleanout, a loose or missing plug can result in the same kind of poor operation. Finally, the design on the right will work. It follows the conservative design equation shown, ensuring that trap height and depth are adequate to maintain a water seal. This trap design requires a high drain opening, but it seals properly and meets the requirements of the standard. Section 511 indirectly addresses coil cleanability. When a cooling coil gets dirty, higher coil air velocities can lead to water droplet carryover, as well as increased coil pressure drop. This problem can be reduced by keeping the coil clean. There are not standards to define the relative ease of cleaning for differing coil geometries, but it's easier to clean a coil from one side if its geometry, in terms of number of rows and fin spacing, results in a 0.75 inch or less pressure drop. Coils with higher pressure drops can be used too if access for cleaning is provided both upstream and downstream of the coil. Section 512 applies to humidifiers and water spray systems. They must be designed to reduce the entry of waterborne contaminants and chemicals into the airstream. Consequently, the standard requires the use of potable water for these devices, and it requires that any downstream devices be located beyond the droplet absorption distance as defined by the humidifier manufacturer. Section 513 addresses access to air distribution equipment and components. Of course, dirt can accumulate in the air distribution system, and accumulated dirt can lead to odors and, in some cases, microbial growth. To ensure that it can be cleaned, inspected, and maintained, the standard requires sufficient clearance around ventilation equipment to allow access. It also requires access doors or panels to allow inspection, maintenance, and calibration of air system equipment, such as air handlers, terminal units, controllers, and sensors. It requires access doors or panels to allow for cleaning, routine maintenance, or calibration of air system components, such as coils, filters, drain pans, fans, and humidifiers. Section 514 reduces water intrusion into the building, as well as unplanned condensation on cold surfaces. The building envelope, including walls and roof, must be designed using a weather barrier to prevent the intrusion of water and airborne contaminants. And a vapor retarding surface must be installed on the warm side of the insulation to prevent condensation of water vapor within the building envelope. And all exterior joints, seams, and penetrations must be sealed, forming a continuous barrier to prevent air leakage. Also, any cold surface within the building, including ducts, cold water pipes, and condensate pipes, must be insulated to prevent surface condensation. The insulation must include a vapor retarder on the warm side to prevent condensation within the insulation itself. Section 515 addresses buildings with attached garages. If a parking garage is attached to an occupied building, the building design must include provisions to reduce the transfer of exhaust fumes into the occupied areas. The garage exhaust system must be designed to ensure that the garage is at a negative pressure with respect to the building, or an airlock vestibule must be provided to prevent free flow of air from the garage into the building, or some other design approach must be employed to limit the entry of vehicle exhaust. Section 516 addresses classes of air. Air from different zones or locations within the building must be designated according to the expected level or type of contaminants in it. The standard identifies 4 air classifications ranging from air with low contaminant concentration to air with highly objectionable or potentially harmful contaminants. Air classifications are listed for each occupancy category in Table 6.1. Once designated, air movement within the building must comply with some simple recirculation limits. For instance, the standard allows Class 1 air to be transferred or recirculated to any space or location. But Class 2 air must only recirculate to other Class 2 or to Class 3 spaces with the same or similar purpose. Class 3 air is only allowed to recirculate within the space of origin. And Class 4 air must be exhausted to outdoors without any recirculation at all, even within the space of origin. Finally, Section 517 addresses airflow in buildings that allow smoking in some areas but prohibit it in others. To reduce the transfer of environmental tobacco smoke, ETS areas must be at negative pressure relative to ETS-free areas. The areas must be separated using walls with doors. Separate air handlers must be used for ETS and ETS-free areas, and air must be exhausted from ETS areas. Signs must be posted to indicate areas that might contain environmental tobacco smoke. Fewer and fewer buildings allow smoking indoors, so these ETS requirements are becoming less and less important to building designers. And remember, Standard 62.1 doesn't include any minimum outdoor airflow requirements for zones with environmental tobacco smoke.
Thanks, Dennis. In this next segment, Paul is going to revisit the zone calculations of the ventilation rate procedures and demonstrate how the standard allows design calculations to be based on average zone population. Paul?
For any zone with a fluctuating number of occupants, design calculations can be based on average zone population rather than peak zone population. Average population is calculated over a defined time period. The equation for calculating the averaging time period is based on the volume of the zone and the breathing zone outdoor airflow that would be required for peak population. Averaging zone population results in lower breathing zone outdoor airflow, lower outdoor air intake flow, and potentially smaller capacity equipment. Let's use my previous 2 examples to see how this works. My example office was 1,000 square feet with a peak population of 5. If the ceiling height is 10 feet, the volume of that zone is 10,000 cubic feet. Recall that for the peak zone population, the required breathing zone outdoor airflow would be 85 CFM. So solving this equation, we find the averaging time period for this office is about 6 hours. This slide is the expected occupancy profile for our office space example. At least one person is in the office from 6 a.m. until 6 p.m., and the maximum number of occupants is 5. But the actual number of people fluctuates throughout the day. The highest average population over a 6-hour time period is 3.8. So, when solving our breathing zone equation again, this time using our average population, we find the required airflow drops to 79 CFM compared to 85 CFM when based on peak population. Let's see what happens in the second example, the conference room. It's also 1,000 square feet with the same ceiling height, but the peak population is 17. When solving for the averaging time period for this zone, we get 4 hours. Even though the volume of the conference room is the same as the office, the higher peak outdoor airflow, 145 versus 85, reduces the allowable averaging time. Looking at the expected occupancy profile for the conference room, again, we see that even though the maximum number of people is 17, the actual number of occupants fluctuates. The highest average population over a 4-hour time period is 9.75. And our breathing zone airflow based on this average population drops to 109 CFM, compared to the original 145 CFM when it was based on peak population. So you can see, The more the population varies, the greater the impact of averaging. In addition, the taller the ceiling height, the longer the averaging time period, and the greater the impact. Of course, the hard part about this is estimating the occupancy profile. It's probably easier to do in some zones than others. For instance, profiles for classrooms or churches may be easier to estimate than for offices, theaters, or stores. For many zones, designing for average population lowers intake airflow and reduces equipment capacity, but predicting that population profile can be quite challenging. It's also important to note that averaging for the sake of design calculations is not the same as resetting intake airflow for part load conditions.
Thanks, Paul. In this last segment, John is going to revisit the system calculations of the ventilation rate procedures and go through the steps for calculating zone ventilation efficiency for systems with a secondary recirculation path. John?
To review what Dennis shared during the main program, in a system with a secondary recirculation air path, some of the air supplied to each zone is recirculated from other zones without directly mixing with outdoor air at the intake. The most common examples are VAV systems that use fan-powered VAV terminals, which draw recirculating air from the ceiling plenum. Two-fan dual-duct VAV systems are another example. We'll use a series fan-powered VAV system to illustrate the calculations in our example. In this system, one air handler brings in outdoor air at a central location and mixes it with recirculated air from all the zones. In addition, each fan-powered VAV box recirculates air from the ceiling plenum, providing a secondary recirculation air path to consider. Standard 62 gives you credit for the unused or excess outdoor air that recirculates, both centrally and locally. Again, the ventilation rate procedure begins with zone calculations and proceeds to system calculations. We'll use the same three-zone example, so most of the steps are the same. The main difference will be in step 3, when we calculate ventilation efficiency for each zone. So, step 1 of the system calculations is to determine the zone outdoor air fractions. In a series fan-power VAV system, discharge airflow to the zone and primary airflow from the main duct are not always equal. As the space cooling load decreases, primary airflow decreases, and more of the discharge air is recirculated air from the ceiling plenum. Remember, Z sub PZ is defined as the ratio of the zone outdoor airflow to the primary airflow delivered to the zone. So this fraction is higher when zone primary airflow decreases. For this example, we'll take the same conservative approach that we did for the single path VAV system and use the minimum primary airflow setting of the fan-powered VAV box when calculating the zone outdoor air fraction. For zone 1, the design discharge airflow is 2600 CFM, and the minimum primary airflow setting is 650 CFM. So the worst case outdoor air fraction for zone 1 is 0.46. 300 CFM of outdoor air divided by 650 CFM of primary air. Solving for the other zones, we find that the outdoor fractions vary from 0.46 to 0.5 for our example. With the zone fractions calculated, the next step is to determine the uncorrected outdoor air intake, V sub OU. Again, this is the same as the single path VAV example, so I won't spend much time here. Taking credit for occupant diversity, the uncorrected outdoor air intake is 1000 CFM for our example. When a system has two recirculation paths, the method for calculating system ventilation efficiency in Appendix A is similar, but more complicated than for a single path system. First, we determine the average fraction of outdoor air in the system, X sub S. Again, this is the uncorrected outdoor air intake divided by the total system primary airflow. The calculation of zone ventilation efficiency has a few more terms that we'll have to look at. These terms help account for the fact that unused outdoor air enters the zone through both of the recirculation paths. Finally, just like for the single-path systems, the system ventilation efficiency is equal to the smallest zone efficiency. Now to calculate X sub S in step 3A, we need to know the total system primary airflow. Like in the previous example, load calculation software calculated the design primary airflow, or block airflow, of the system to be 6,000 CFM. So the average outdoor air intake fraction for this system is equal to the uncorrected intake, which we calculated to be 1,000 CFM, divided by the total primary airflow for the system, which is 6,000 CFM. So X sub S is equal to 0.17. Step 3B is to determine the ventilation efficiency for each zone. For systems with a secondary recirculation air path, Appendix A provides this equation for zone ventilation efficiency. It uses X sub S and Z sub PZ, which we've already calculated. But it introduces 4 new terms: F sub A, F sub B, F sub C, and E sub P. These new terms are used to define the fraction of discharge air that enters the zone through the 2 different recirculation paths. Let's see what they're all about. F sub A is a fraction of discharge air that comes from locations outside the zone itself. Its equation uses the variables E sub P and E sub R. The first one, E sub P, is the smallest fraction of discharge air that's comprised of primary air. It's calculated by dividing the minimum expected primary airflow by the discharge airflow. For the series fan power VAV system, in our example, we're assuming discharge airflow to the zone is constant. So E sub P will be smallest when zone primary airflow is lowest. Again, we'll take the same conservative approach and use the minimum primary airflow setting of the fan power VAV box. For zone 1, discharge airflow is 2,600 CFM, and the minimum primary airflow setting is 650 CFM. So at this worst case condition, 25% of the discharge air is comprised of primary air, and the other 75% is locally recirculated from the plenum. Of course, as we discussed during the main program, the lowest expected primary airflow might be higher than the minimum setting of the box. The second term, E sub R, accounts for the quality of the locally recirculated air. That is, how much of the air that is recirculated locally is a mixture of air from all zones served by the system, rather than just from the zone it's going back into. For example, if recirculated air from a zone is ducted directly to the intake or inlet of the fan power VAV box serving that same zone, the recirculated air in the secondary path is the same quality as the air within the zone itself. In this case, E sub R would be 0. However, in most fan power VAV systems, the locally recirculated air is drawn from an open ceiling plenum. Then the rest of the air returns to the air handler through an opening above the ceiling. In this case, E sub R will be closer to 1 if the VAV box is located near the central return air opening, like it is for zone 3 in our example here. At this location, the locally recirculated air is a uniform mixture of air returning from all the zones. But E sub R will be closer to 0 if the VAV box is located directly over the return grill of the zone it serves, like it is for zone 1 here. At this location, the locally recirculated air is mostly made up of air returning from that same zone. Now, Standard 62 does not currently provide a default or calculation method for E sub R, so it's left to the designer's judgment. However, example 6-F in the user's manual provides some guidance based on an ASHRAE research project that measured E sub R in a real building, with fan power boxes in various locations. For our example, we'll assume E sub R to be 0.3 in zone 1, 0.5 for zone 2, and 0.9 for zone 3. As a side comment, for a dual fan, dual duct VAV system, all the recirculated air returns to the central air handlers. So E sub r would be equal to 1 for all zones in that type of system. Now, getting back to our series fan power VAV example. With our assumptions for E sub r, we can now solve the equation to calculate F sub a for each of the 3 zones. Zone 1, which has the lowest value for E sub r, results in the lowest value for F sub a at 0.48. For Zone 2, it's 0.63, and 0.93 for Zone 3. The next term, F sub b, is the fraction of discharge air that comes from the primary airstream. This term is the same as E sub p, the primary air fraction that we calculated earlier. For our example, this was 0.25 for all 3 zones. The last term, F sub c, is the fraction of outdoor air that comes from sources outside the zone, not recirculated from within the zone itself. This accounts for any outdoor air that bypasses the breathing zone when zone air distribution effectiveness is less than 1. For our example, during the cooling mode, zone air distribution effectiveness is 1 since the diffusers and return grills are both installed in the ceiling. With an E sub z of 1, F sub c ends up equaling 1 for all 3 zones. Now note that if we were to analyze this same system during the heating mode, E sub z might be 0.8 rather than 1. This would indicate that some of the discharge air is bypassing from the supply diffuser to the return grill. And then F sub c would be less than 1. But we'll keep going on our example calculations for the cooling mode. Here, with these new variables all figured out, we can now complete step 3b and calculate the ventilation efficiency for each zone. Solving this equation in our example, we find a zone ventilation efficiency of 0.85 for zone 1, 0.88 for zone 2, and 0.91 for zone 3. In step 3c, system ventilation efficiency is then equal to the worst case or lowest zone ventilation efficiency. That's 0.85 in our example, the efficiency for zone 1. Now, with system ventilation efficiency calculated, the final step is to calculate the required outdoor air intake for the system. As with the single-pass system, this is calculated by dividing the uncorrected outdoor air intake, which is 1,000 CFM for our example, by the system ventilation efficiency of 0.85. So the required outdoor air intake is 1,180 CFM. It should be pointed out that the standard does not require you to use Appendix A for these dual-path systems. As long as the largest zone outdoor air fraction is less than 0.55, you could choose the much simpler approach of looking up system ventilation efficiency in Table 6-3. However, realize that the default values in that table do not account for the unused outdoor air in the secondary recirculation path. So the result will be a higher intake airflow. Quite a bit higher in our example, 1,540 CFM if using Table 6-3 versus 1,180 CFM when using the appendix. Alternatively, I suppose you could use Appendix A, but choose to use the simpler single-path equations. That would typically result in a lower intake airflow than the table, but still higher than with the dual-path equations. While these other approaches are simpler, they do not account for the higher system ventilation efficiency that results from secondary recirculation. Now, as we mentioned in the main broadcast, ASHRAE includes a spreadsheet tool when you purchase the standard 62.1 user's manual. This spreadsheet contains the equations for both single-path systems and systems with a secondary recirculation path. In addition, TRACE 700 can also perform these system ventilation calculations for most common systems with secondary recirculation paths.
Well, that wraps up our supplemental content on ASHRAE 62.1. Thanks to our presenters, and thank you for joining us.